Here we go on 12.3, talking about concentration of solutions. And what we are specifically looking at in this short video here is talking about the definition of concentration as well as what molarity and molality are. We're going to get those equations of molarity and molality to calculate these values. And then we're going to talk a little bit about how to prepare a solution. We have a short clip to show you on that. And then really use this dilution equation in solving these types of problems. And then the last is calculate the percent concentration or the same concentration in parts per million. So let's go ahead and talk about concentration here. And basically you need to know that it's basically measuring the amount of solute that is dissolved in a solvent. It's often measured in grams of solute and again per milliliter of solvent. So that is basically we're going to find out that's also molarity here once you do a simple mole conversion. So we already spoke briefly about dilute and concentrated, but this picture kind of tells it really quite well in that a concentrated solution obviously has more solute dissolved in the solution. A dilute solution has less solute dissolved in the solution. These are the equations that we're going to be using here, and it says 3 basic ways, but there's a few more because there's variations of these equations. And really you can get these copied down. It's percent concentration of a solute. So again, what's being dissolved in the solution? And the equation is just simply grams of solute over grams of the solution. And you can see here the solution is really the solute plus the solvent. So an example is salt water. So the grams of the solute would be grams of salt. And down here, this would be, well, how much salt in the amount of water that you used. And you would just add those together. And then obviously multiply it by 100 to make a percent. You can do the exact same to find the percent concentration of the solvent, so what's doing the dissolving. If you want to know, all right, how much water is in the solution? Well, same thing, grams of water over grams of the solution times 100. So that's very easy. Molarity, this is very important. This is moles of solute over volume of solution. So it's moles per liter. The symbol here is very important to know. It's a capital M, whereas we're going to look at molality, it's actually a lowercase m. So that's a big difference. You really need to know the difference between the two symbols here. And molality is simply moles of solute, so that stays the same, but the denominator changes in that it's kilograms of a solvent. That's a little different than liters of solution. And while we're talking about kind of concentrations here, we also have a parts per million concentration, which is ppm, parts per million. The exact same thing as percent concentration, except instead of multiplying by 100, you multiply by a million. And this really deals with very minute and small particles. When you have to have a lot of it present in order to have some substance, this is when we would use parts per million. And then the dilution equation. And again, we're going to put these all to use, but just get them down right now. M1V1 equals M2V2. Make sure you know what M and V stand for, molarity and volume. And obviously those are your initial and they're your final volumes. So let's put this to use here and looking at what molarity is. So we have here the molarity problem or the equation. Capital M is moles of solute over liters of solution. And really what we're doing is we're controlling things here in when we were making a solution. So this is a volumetric flask. And you guys do need to know that this is a volumetric flask because we use it to make solutions. And what it does right here, it only has one measurement. So it only measures for one amount, okay? So this one here is actually 1,000 milliliters or 1 liter. But that's a special use because it measures exactly that amount. So our problem is, what is the molarity of a 50 milliliter solution that is made of 4.6 grams of sodium chloride? So we're going to attack this problem here by identifying our givens and unknowns. So I'm given 50 mils of a 4.6 gram solution of NaCl. So let's write this out here, and I'm asked to find the molarity. So my unknown is M. Volume is 50 milliliters. I need to convert that to liters because molarity is liters of solution. So I get 0.05 liters. And then grams of solute, I need to convert to moles. So I do a simple mole conversion. So I'm going to convert here my 4.6 grams, cancel grams. Remember, this is from the periodic table right here, right? PT is where you're getting the molar mass. And I get 0.079 moles. So then molarity is moles per liter, 0.079 moles per 0.05 liters. And I'm going to simply divide those to get my final molarity. After dividing this out, you end up with 1.58 molar, or M as the right unit. And that's calculating molarity. Let's go ahead and look at a molality example here. So molality is actually moles of solute per kilograms of solvent. Now, that's a little different because we're in kilograms of solvent. So we're going to look at here how to calculate a 0.5 M, so small m indicates molality, solution of copper sulfate pentahydrate. Well, the steps here, if you were asked to how do you actually do that, is, well, we first need to find the mass of the solution needed. Second, let's just use 1 kilogram of solvent because dividing by 1 is very, very easy. And the last is going to be, once you divide them, that's your 0.5 molar solution. So again, I'm kind of going to list over here my variables. I'm given the molarity, or the molality, excuse me, of 0.5. I'm asked really to find the moles of the solutes because I need to know how much there is, and then the kilograms of the solvent was also provided for me. So let's substitute this into my molality equation. So I have 0.5 M equals moles of solute, because that's your unknown, over 1 kilogram of the solvent. So to get moles, I'm going to simply solve here by multiplying each side by 1, and that cancels. And then what I do to one side, I do to the other, and I end up with 0.5 equals my moles of solute. Right? So that's your copper sulfate pentahydrate. Now, to get this up here to actual grams, if it wants the grams, that's a simple conversion because we've done this before. You just have to do a mole conversion of your copper sulfate pentahydrate and set up our train tracks to go ahead and convert that into grams. So I have moles on the bottom, and I'm going to grams of copper sulfate pentahydrate. So I'll grab my periodic table, add up 5 waters plus CuSO4, and my mass is going to be 249.71 is the molar mass. Go ahead and multiply, and I end up with 124.86 grams, which is what we had there, and that's finding the grams of solute needed for this molality calculation. All right, the next thing that we're moving on to is actually doing the percent concentration and taking a look here at how to find percent concentration. And again, you need to remember what the percent concentration equation is, so we can always go back in our notes here to our reference sheet and see that percent concentration is grams of solute over the grams of solution, so that maybe we can jot that down here as being something that we would want for good use, is knowing that percent concentration is going to give you the grams of solute over grams of solution. So in this problem, you're asked to find the percent concentration of 55 grams of potassium iodide in 350 grams of water. Well, let's identify our variables, our givens and unknowns here. We actually have percent concentrations unknown. If 55 grams of water are in 350 grams of water. So let's set this up here. I'm still unknown on my percent concentration. I'm given grams of solute, which is 55 grams of potassium iodide. and I'm dividing that by the 350 grams of water, but it needs to be the whole solution. So I have to add in the 55 kilograms of potassium iodide also. So it's really 55 divided by 405. Times 100 obviously makes it a percent. So I'll add that into our equation there, times 100. So let's go ahead and type that in our calculator to get the correct answer. And we get 13.6% there as our mass of the, or as the percent concentration for the substance. So it's second example problem, finding the mass of sodium hydroxide in 21.5% concentration solution, assuming that we have 40 grams of the solution present. So basically, let's identify our givens and our unknown here. We're asked to find the solute, in this case, what's being dissolved, the sodium hydroxide. We're given percent concentration, and we're asked, and we're also given the grams of the solution, which is, again, the solvent plus the solute. So plugging this into my equation, 21.5% equals the grams of the solute, which is your actual unknown in this case, divided by the grams of the solution, and obviously times 100. So to get rid of the 100, all we have to do is basically, if I divide by 100 and I divide the percent by 100, makes it my decimal. So now I'm left with 0.215 equals the grams of solute. And I can also bring the 40 over, so I'm just going to multiply each side by 40. And over here, I end up with 40 times the 0.215. So my final answer for grams of solute ends up being 40 times 0.25, 215, and we get 8.6 as our answer. And that's your grams of solute, so NaOH, sodium hydroxide. It's pretty simple there on that one. And then the last problem that we want to go ahead and take a look at is to find the concentration in parts per million if there is 0.00123 grams of sodium bromide in this many grams of solution. So again, let's identify our variables here. We are provided with the grams of solute and the grams of solution, and I'm asked to find parts per million. Remember, look back on your equation list. The parts per million is the same thing, grams of solute divided by grams of solution times a million, though. That's what makes it parts per million. So my ppm is my unknown, so I'm leaving that as such. The solute is 0.00123 grams, and the solvent is 1,683 grams. And I'll multiply that by 10 to the 6th. So that we should end up with parts per million is going to be this divided by the denominator times 1 million. Calculating that out, we end up with 0.731 ppm, parts per million, would be the correct label for that example problem. And then the last thing that we're going to talk about here is our dilution problems. So actually remember the dilution problem here equation is simply M1V1 equals M2V2, and we're going to calculate out here basically how to dilute a solution. So let's dive right in. We have a solution that is 0.5 molar, capital M is for molarity, potassium bromide. If we use 20 mils of it, if you dilute it to 100 mils, what's your new molarity? So I have a beaker. It has 20 mils of it in there. I'm going to fill the beaker up to 100 mils total. And once I do that, I want to know what the new concentration is, what's the new molarity. So I know that I'm using the M1V1 equals M2V2 equation because I'm given this is my M1, that'll be my M2, and then this is my V1 here, and this is my V2. So I'm going to plug these variables into the equation. So I end up with 500 times 20 equals M2 times 100. get M2 by itself, I need to divide each side by 100. So I divide each side by 100, and I end up with M2 as being 0.1 molar. So it's pretty simple there for the molarity calculation. Let's go ahead and look at a second dilution problem. We're asked to find what volume of water would be added. Now this is a little different because it's asking how much would I add to a 16.5 milliliter solution of 0.0813 molar solution of sodium borate to get a new molarity of 0.02. So that's the equation I want to use. Again, we're going to identify our given and unknowns here. I need to find what volume added. So that's unique because I need to know how much am I going to add. The volume initial is 16.5 at 0.0813 molar, and I'm trying to get a new concentration of 0.02. So dilute it a little bit. So I'm going to pour some water in. So what I kind of did here was, let's think about this. I have a beaker. It has 16.5 milliliters of water, and that's initially. I'm going to add some water to it, right, to get it up to a new amount. That's your final volume that we're going to find. We actually need to find the difference here to determine how much we actually added. So let's see how we got this 67.07 value. I'm given M1 V1 equals M2 V2. Let's substitute in. There's M1, there's V1, there's M2, V2 is unknown. I need to get V2 by itself, so I'm going to divide each side by the 0.02 as here, and this is how I get the 67.07. So right now my beaker has 67.07 as the final volume. But the question doesn't ask what's the final volume. It says what volume is added. So I need to figure out, well, what's the difference here? So from 67, I'm going to subtract the initial amount, which is 16, and that means you actually need to add 50.57 milliliters to the solution in order to get it diluted to the 0.02 molar. So hopefully that wasn't too confusing for you as we wrap up here our dilution equations.